I'm Dr. Dhinakar, professor in the Department of EC, Bharat Institute of Higher Education Research. Today, I'm going to topic on transmission and reflection of plane waves at the boundaries. So it comes under the subject transmission line and waveguides, whereas the course code for the particular subject is U18Pcec502. Now let's get into the topic of transmission and reflection of plane waves at the boundaries. Plane wave propagation at arbitrary angle. Plane waves are not normally incident. So now we must consider the general problem of a plane wave propagating along a specified axis that is arbitrarily relative to a rectangular coordinate system. The most convenient way is in terms of the direction cosines of the uniform plane wave. The equiphase surfaces are planes perpendicular to the direction of propagation. Let us see some of the definitions that is involved with this topic. First of all, let's happen to see what is an uniform plane. A free space plane wave at an infinite distance from the generator, having constant amplitude electric and magnetic field vectors over the equiphase surfaces. So that is what we call it as a uniform plane. Next, we go for equiphase surface. What is an equiphase surface? Any surface in a wave over which the field vectors of a particular instant have either 0 or 180-degree phase difference. So that one is what you call it as equiphase surface. For a plane wave propagating along the z-axis, we do have a formula of E of z is equal to Em into e power minus j beta z into a power x, where Em is that is the amplitude of the waveform, where ax is the unit vector. This equation states that each z equals to a constant plane will represent an equiphase surface with no spatial variation in the electric or magnetic fields. In other words, what it says that dou by dou x is equal to 0, which is equal to dou by dou y for a uniform plane wave. So it will be necessary to replace z for a plane wave traveling in an arbitrary direction with an expression when put equal to a constant. That is beta z is equal to constant. So that will result in an equiphase surface. The equation of an equiphase plane is given by beta into r is equal to beta into n suffix beta into gamma. So the radial vector r from the origin to any point of the plane and beta is the vector normal to the plane is shown in the figure. So there you see that you could see the figure where you got three axes, x-axis, y-axis, and z-axis, and there the radius vector is given as a small r, and there you could see a line of PW that has been enclosing along the y-axis and z-axis, thereby forming a triangle, and we have got this angle of theta y, where the radius vector goes on to make with the y-axis, and theta z is the angle between the radius vector and the z-axis. So that's how this the diagram has been depicted, and various details from the diagrams are visible. So as you can see from the figure, the plane perpendicular to the vector beta is seen from its side appearing as a line PW. That is, you see that there is a plane that has been represented as a line PW in the figure. The dot product n beta dot r, the dot product n beta dot r is the projection of the radial vector r along the normal to the plane. So generally we talk about the dot products and all. We are talking about the projection of a vector onto the other. So here nb dot r is the projection of the radial vector r along the normal to the plane, and will have the constant value OM for all points on the perpendicular on the plane, for all points on the plane. The equation beta dot r is equal to constant is a characteristic property of a plane. The equation beta dot r is equal to constant is a characteristic property of a plane perpendicular to the direction propagation beta. The equiphase equation is beta dot r is equal to beta x of x plus beta y into y plus beta z into z. That is equal to beta into cos theta x into x plus cos theta y into y plus cos theta z into z. So that is overall is equal to constant. R is equal to x of ax plus y of ay plus z of az. There is beta is equal to beta x into ax plus beta y into ay plus beta z into az. Theta x, theta y, theta z are the angles the beta vector makes with zy and z axis respectively. And definition. Transverse electromagnetic wave. So the definition for a transverse electromagnetic wave is the electromagnetic wave having electric field vectors and magnetic field vectors perpendicular to the direction of propagation. Then we call that a particular wave is a transverse electromagnetic wave. Whenever we do have electric and magnetic field vectors or perpendicular to the direction of propagation, then we can call that particular electromagnetic wave as a transverse electromagnetic wave. And now here in the diagram, you could see this H is perpendicular to E, where H is the magnetic field intensity and E is the electric field intensity. As both of them are perpendicular to each other, both E and E are perpendicular to the direction of propagation constant beta. Therefore, the expression for E and H are E is equal to Em into e power minus j beta into R. There is electric field intensity. Then magnetic field intensity H is equal to n beta to the power E divided by eta. The unit vector n beta along beta and eta is a wave impedance in the propagation medium. See in the figure 6.2 for illustration of orthogonal relationship between E and H and the direction of the propagation. There in the figure you see that you could see the relationship, orthogonal relationship between electric field intensity and the magnetic field intensity. That one has been shown in the figure there. And as well as both the things has been linking to the direction of the propagation. Okay, here you see that the diagram has been spread along three different axes, x-axis, y-axis, and z-axis, where you could see that we could see various things that are some a lengthy line or a lengthy line being represented as a vector that is small p is equal to capital P into H, that one representing the power density flow. And there you see that at a particular point on the line P, that point has been resolved into two components, that is magnetic field intensity H and electric field intensity E. So they make out orthogonal components. And here you see that this vector P is made out along the unit vector n beta. So whereas unit vector n beta is along the radial vector. Therefore, the radial vector R is supposed to have the unit vector n beta, and when it is projected over a lengthy line, we do have that one as a vector small p that is equal to capital P into H. That one is supposed to give the power density flow. And now the plane where all these things are spread out, we can call it as plane of constant phase. Okay, so this particular diagram can give out the relationship between orthogonal relationship between the electric field intensity E and magnetic field intensity H, and of course the direction along with the propagation takes place also. Reflection by perfect conductor, arbitrary angle of incidence. So what is the reflection? by a perfect conductor. Okay. By decomposing the general problem into two special cases, we can simplify our analysis. Number one, E field. E field, that is electric field, is polarized in the plane formed by the normal to the reflecting surface in the direction beta I of the incident wave. The second one, E field, that is electric field, is perpendicular to the plane of incidence. The plane formed by the normal to the reflecting surface and the direction of propagation beta is known as the plane of incidence. The general case can be considered as a superposition of the two cases. That is, E is parallel to the plane of incidence, E is perpendicular to the plane of incidence. That is, uh, by superposition of two cases, we see that we do have E is parallel to the plane surface and E is perpendicular to the plane of incidence. And now you could see in the diagram, E field parallel to the plane of incidence. You see that the perfect conductor being put out there, and you just see here E field in the sense electric field, and here we do have magnetic field H, and we see that we got have the propagation constant beta. See that there we have got all these things. Incidenting is just incident on the perfect conductor, and on the right hand side you see that all the reflected waves on the right hand side. Of course, you see that the electric field intensity is perpendicular to the magnetic field intensity, which is along the line of propagation. So you see that as these things is getting incident on the perfect conductor with an angle of theta 1, then they get reflected with an angle of theta r, where you see that it's of course reflected on the right hand side, and you could see that there the components get resolved into three components. That is electric field intensity. Reflected electric field intensity is perpendicular to magnetic field intensity Hy, whereas Hy and beta r, that is propagation constant, reflected propagation constant, and magnetic field intensity Hy seems to be on the same line. That is you could understand that E field parallel to the plane of incidence. You see that as E field from the diagram, you could clearly understand that E field is parallel to the plane of incidence. As you could see that where is the plane of incidence lie, and you could see the electric field intensity E also. The figure shows an incident wave polarized with electric field E in the plane of incidence and the power flow in the direction of beta I at angle theta I with respect to the normal to the surface of the perfect conductor. The direction of propagation is given by the Poynting vector at the beta I. E and H fields need to be arranged so that beta I is in the same direction as E to the power I and H to the power I at any time. The magnetic field is out of the plane of the paper. Therefore, H is equal to Hy into AY for the direction of the electric field shown. There is no transmitted field within the perfect conductor. However, there will be a reflected field with power flow at the angle theta r with respect to the normal to the interface. To maintain the power density flow, E of r and H of r will be in the same direction beta of r, as the expression for the total electric field in free space is capital E is equal to E to the power I plus E to the power r, which that refers to electric field intensity incidence and electric field intensity reflected. That is capital E is equal to E power I plus E power r, that is equal to Em to the power I into E power minus j beta I into r plus Em to the power r into E power minus j beta r into r. That is, beta I into r is equal to beta into cos theta I into az plus sin theta I into ax. The whole thing gets enclosed in the bracket into x of ax plus y of ay plus z of az. So that this equation probably is getting simplified to beta I dot r is equal to beta into x of sin theta I plus z of cos theta I, which further gets simplified as the same thing can be applied for the reflected wave also. Therefore, beta r dot r is equal to beta into x sin theta r minus z cos theta r. So therefore, the total electric field has x and z components. There is the total electric field can be said to have that x and z components also. Therefore, E of x comma z is equal to, there is electric field intensity in the x direction has got both x and z components. Therefore, that is E of x comma z is equal to E of m to the power I into cos theta I into e power minus j beta I into r plus em to the power r into cos theta r into e power minus j beta r into r. Then we do have the z component of electric field intensity, that is E of z is equal to x comma z is equal to minus e power m to the power I into sin theta I into e to the power minus j beta r into r plus em to the power r into sin theta r into e power minus j beta r dot r. That is E of x at z is equal to 0, that is equal to E of m to the power I into cos theta I into e power minus j beta I into r minus E of m to the power r into cos theta r into e power minus j beta r into r is equal to 0. So now you see that as the equations get simplified further, we can have E of x at z is equal to 0 is equal to E of m to the power I into cos theta I into e power minus j beta x into sin theta I minus E of m to the power r into cos theta r into e power minus j beta x into sin theta r is equal to 0. Then as we move on, we get to find out that theta I is equal to theta r, that is the angle of incidence is equal to the angle of reflection. The total magnetic field, that is magnetic field which is represented by the letter H, is given as the total magnetic field. The total magnetic field is H of x of z. That is magnetic field intensity. H is given in terms of the variables x of z is equal to H of y in terms H of y of x of z into a of y, that is equal to H of y to the power I of in terms of x of z into ay plus H of y to the power r of x of z into a power into ay, where ay is the unit vector along the y direction. Use the relation H is equal to n beta to the power e over eta. So n beta, you know, that is the unit vector along the propagation constant, to the power e over eta for each of the incident and reflected fields to employ the expressions x and z components of the incident and the reflected electric fields. Therefore, H of I is equal to n beta I over eta to the power e of I. So that one has been given in the matrix form, that is equal to, that is 1 by eta, the matrix, the determinant opens, whereas the first, under the first column we do have ax sin theta 1 sin theta I, then e of m to the power I into cos theta I into e power minus j beta into sin theta I x plus cos theta I z. Whereas on the second column we do have ay 0 0. On the third column we do have az cos theta I minus E of m to the power I sine theta I into e power minus j beta into sine theta I x plus cos theta I z. Then the solution of the determinant, the only non-zero component of hi is the ay component given by, that is h of I is equal to 1 by eta into ay into em cos squared theta I into e power minus j beta into sine theta I x sine theta I of x plus cos theta I of z plus em to the power I into sine squared theta I into e power minus j beta into sine theta I of x plus cos theta I of z, that is equal to e of m to the power I divided by eta into e power minus j beta into sine theta I of x plus cos theta I of z to the into a of y. The reflected magnetic field is given by h of r is equal to e power m by eta into e power minus j beta into sine theta I of x minus cos theta I of z into a power y. Therefore, the total magnetic field h of x of z is h of x of z is equal to ay into 2 to the power e of m em divided by eta into cos beta z into cos theta I into e power minus j beta x into sin theta I. The average power flow parallel to the conducting surface is P average x of z is equal to half real into e, e of h, that is equal to half of re into determinant ax ay az ex 0 ez 0 hy 0. The cross product yields two components, one in the x direction, one in the y direction. P average is equal to half of re is equal to half of re into minus e of z h of y into a of x plus e of x into h of y into a of z. The expression of P average will reduce to P average in terms of P average of x of z is equal to half real into minus e of z into hy into ax. Glancing incident. Glancing incident in the sense as angle of incidence, that is theta I, approaches 90 degree. Therefore, P average becomes 2 into e of m to the power I is to the whole square divided by eta into ax. The power flow will be at its maximum. Normal incidence, that is theta I is equal to 0. As theta I becomes 0, P of x, P of average is equal to 0. Average power flow perpendicular to the conducting surface is 0 because the average pointing vector is 0 at that direction. That is, P of z average is equal to half of real of E of x into h of y, that is equal to 0. Why? Why? Because E of x is multiplied by j. Therefore, E of x and h of y are out of phase by 90 degree. Therefore, a traveling wave pattern occurs in the x direction because the incident and the reflected waves travel in the same direction. The standing wave pattern will be observed in the z direction because the incident and the reflected waves travels in the opposite directions. The locations of zeros of the Ex field can be found by letting sine beta z cos theta phi is equal to 0. At a distance z from the conducting plane given by beta z into cos theta I is equal to n pi, where z is equal to n into lambda by 2 is 2 cos theta I, where n is given by 0, 1, 2. Reflection and refraction at plane interface between the two media. That is oblique incidence. As we could see from the figure, we will happen to see from the figure 6.7, it shows you two media with electrical properties, emissivity 1 and mu of 1 in medium 1 and 2, and emissivity 2 and mu 2 in medium 2. Here, a plane wave incident angle with theta I on a boundary between the two media will be partially transmitted into and partially reflected at the dielectric surface. The transmitted wave is reflected into the second medium, so its direction of propagation is different from the incident wave. The figure also also shows two rays for each of the incident, reflected, and transmitted waves. A ray is a line drawn parallel to the equiface surfaces, and the line is along the direction of propagation. And you could see the things from the diagram where you see that you've got E emissivity 1 and mu 1, emissivity 2 and mu 2. You've got permittivity of the medium 1 and the permittivity of the medium 2, where you see that the waves travel over the first medium and gets reflected at the second medium. Therefore, there seems to be some angle of incidence and angle of reflection, and there seems to be somewhat different in the way in which the incident rays travel after it gets reflected by the medium. The diagram is a clear indication of all the concepts. The incident ray 2 travels the distance CB, while on the contrary, the reflected wave 1 travels the distance EAE. That is, as the media happens to be different, the incident and the reflected wave seems to be somewhat different from each other. For both AC and BE to be the incident and the reflected wave forms or planes of equiphase, the incident wave should take the same time to cover the distance EAE. The reason being that the incident and the reflected wave rays are located in the same medium, therefore their velocity should be equal. CB by V1 is equal to AE by V2. For this assumption of their velocity should be equal, we come to a point that AB sin theta I is equal to AB sin theta R. With this being the case, then it follows that theta I is equal to theta of R. That is, the angle of incidence should be equal to the angle of reflection. So what should be the relationship between the angle of incidence and the angle of refraction, theta R? And of course, it takes the incident ray the equal amount of time to cover the distance CB as it takes the refracted ray to cover distance AD. Therefore, CB by V1 is equal to AD by V2, and the magnitude of the velocity V1 in the medium 1 is that one given by V1 is equal to 1 by root of mu1 into epsilon 1. And in medium 2, we do have V2 is equal to 1 by root of mu2 into epsilon 2. Also, CB is equal to AB into sin theta I into and in the next line we do have AD is equal to AB sin theta I. Therefore, we do have CB by AD is equal to V1 by V2 is equal to root of mu2 into epsilon 2 divided by mu1 into epsilon 1. Therefore, as some simplification, we do have sin theta I divided by sin theta R is equal to root of epsilon 2 divided by epsilon 1. And now, as we come to the end of the chapter, here we have seen a lengthy derivations in section of the reflection and theory behind the incidence wave and the reflected wave and what happens in the boundaries and all we saw here in this presentation. And we do get various equations and formulas, and you could see that a relationship between the electric field intensity and magnetic field intensity, and as well as the propagation instant and things happening at the boundary surfaces and all. Thank you. Thank you for listening. Thank you.